Hello everyone and welcome to Fatal Sack. Have you ever tried running an iOS application on your jailbroken phone with a rootless jailbreak like Dopamine or Pale Rain only to be met with a jailbreak detected message or an immediate crash? For instance, in this case, the application detects the jailbreak as indicated by these red cross icons. But what if I tell you that even with these advanced rootless jailbreak detection mechanisms, you can still bypass them and get the app running smoothly on your jailbroken devices? Now you can see that all the detections are passed which are indicated by these green tick marks. Isn't it cool? So, to give you some context about this new rootless jailbreaks, the reason behind these rootless jailbreaks is that Apple has significantly enhanced its security measures, due to which the traditional jailbreaks like Uncover and Check Rain became obsolete, making rootless jailbreaks the new standard. But here's the catch, apps have also evolved. They became smarter at detecting these rootless jailbreaks. So today we will break down some of the most interesting techniques apps use to detect these jailbreaks and explore how we can circumvent these detection mechanisms. For this demonstration, I will be using my iPhone, which as you can see on the right hand side is running on iOS 16.2 and has been jailbroken rootlessly using Dopamine jailbreak. And the techniques I will be showcasing in this video are also applicable to other rootless jailbreaks such as Pale Rain. So we have an application called Jailbreak Detector, and upon launching it, you can see that it uses 10 different methods to detect a rootless jailbreak. And when we click on this detect button, it shows which detections have been triggered, indicated by these red cross icons. Our goal is to analyze each of these detection mechanisms used by the app and then develop a Frida script to work around these detection mechanisms. Okay, and I have uploaded this application to our FatalSex GitHub repository, and you will find the link in the description box below. So if you would like to follow along, pause the video now, download this application and install it on your rootless jailbroken device before continuing. Now, before diving into the analysis, for those who are wondering what the heck is this rootless jailbreak and how it is different from traditional jailbreaks, let me quickly go over this. In a traditional jailbreak like Uncover or Checkrain, the jailbreak has full root access and can modify system files directly, including the root directory and the system partition. This allows deep modifications but also makes jailbreak detection easier for apps, right? Whereas in rootless jailbreaks like Dopamine and Pale Rain, they still provide root access, but instead of modifying the system directories, they redirect everything to a separate environment. This means that you can still run commands as root, install tweaks, and modify the system, but without making permanent changes to system partition. So to make things more clear, let me just go inside the device terminal through SSH root at the rate IP address. Okay, so now I am inside my rootless jailbroken device. Now, what I said about rootless jailbroken devices is that you cannot modify the root directory and the system partitions, right? So let's try by going inside the root directory. Okay, we can list out everything. We have the system partition as well, right? But if you try to modify it, for example, let's try to create a new directory, you won't be able to do that. Cannot create directory, it's a read-only file system. Similarly, if you try to modify the system partition, let's again try to create a new directory, and again we cannot create a new directory because it's a read-only file system. So whatever the changes done by a rootless jailbroken device, for example, the tweaks you want to install, everything will be installed inside this var.jb directory. Alright, you see we are now inside var.jb directory. So you can consider it as a separate environment which gets created by the rootless jailbroken frameworks such as Dopamine or Pale Rain. And this directory is volatile, means once you will restart your device, all the contents in this directory will be gone and your jailbroken status will also be lost. So you have to again jailbreak your device. Okay, so I hope the basic difference between these jailbreaks are clear now. Let's dive into the analysis. The first step would be to extract the IPA file. So I have downloaded the IPA file on this machine already. Okay, if you don't know what an IPA file is, it's nothing but an archive or a zip file containing the application binaries along with other artifacts and resources such as icons, frameworks, mobile provisioning certificates, etc. So we can simply extract this IPA file by first changing its extension from .ipa to .zip like this. Now we have a new file called jailbreakdetector.zip, and now we can simply extract it using the unzip command. So all the contents of this IPA file are now extracted into this new payload directory. Let's see. Yep, we got this new payload directory. Let's go inside it. And here we have the extracted application. And here you will find all the files, artifacts, and certificates which are present inside the IPA. So here is the main application binary, jailbreak detector, and in order to analyze it, we have to open it in a disassembler. I am going to use Ghidra today. So let's import this binary by going to file, import file, and over here we have jailbreak detector. Ghidra automatically identified the file type and the architecture of this binary. Simply hit OK. OK. Now let's start the analysis by double clicking on this binary. And now it's asking you whether you want to analyze this binary or not. Let's hit yes. Leave all these options as it is. No need to modify them. Click analyze. And over here now you can see the Ghidra is analyzing this binary. Give it some time to finish the analysis. Alright, so after finishing the analysis, it will present us with the disassembly of the binary. Now my approach towards reversing a binary always starts with observing the application's behavior by simply running it on the device. This helps me understand how it functions and what areas might be worth investigating in the binary's disassembly. In this case, our main goal is to identify the function or code responsible for jailbreak detection, and by analyzing the app behavior, we can determine what to look for in the disassembly and pinpoint the detection mechanisms. So in the app, we can see these jailbreak detect 1, jailbreak detect 2, jailbreak detect 3, and so on. This suggests that in the binary, we could find some string related to jailbreak. So let's try that. In Ghidra, to search for strings, you have to click on this search menu for strings and then change this memory block types from loaded to all blocks, so that it will look for the string in all the sections of this binary. Click search, and here we have all the strings which are present in this binary. We are looking for string related to jailbreaks, so in the filter you can search for the specific string, and over here we found two strings, and these are also just the bundle IDs of the application, so nothing interesting. Let's quickly scroll through the other strings as well, just to see if there is something interesting. So most of the strings you can see over here are encrypted or encoded in some form, right? This suggests that they might be encrypted or obfuscated. So nothing directly was found in the string section. Let's close this. Now let's try to have a look at the functions. So you can list down all the functions which are present in this binary by going to this window menu and click on this symbol table. Now all the symbols which are marked as external are the imported symbols or functions which are coming from external dependencies or frameworks. Ghidra is smart enough to figure out from which framework these symbols are coming from. So for example, the cc crypt symbol, this is the external function which is coming from this library libsystem.b.dylib. Let's skip the imported symbols for now and see if there is any other user defined function which we can figure out. So all the function names are stripped. Let's move on. These are some of the functions for rendering the UI. So let's just skip them. Then we have some encrypt decrypt function. So this is interesting. This could be related to the encrypted strings which we saw in the string section. Then okay, this looks interesting. So we have this function called run detection methods. By the name of this function, it looks like this function is responsible for calling all the jailbreak detection methods, isn't it? And since this is just a sample application, we are fortunate that this method name is present. Otherwise, we would have first needed to decrypt the strings before potentially uncovering something interesting. Alright, so let's now have a look at this method. So if you just click on this in the disassembly, it will take you to that method. So there are a lot of stack variables being created. Then there are a couple of instructions. Let's see the control flow graph of this function. And there is only a single basic block present, suggesting that there are no branching or conditional statements present in this whole function. So if you closely analyze the disassembly of this function, you will observe that this run detection methods function is calling multiple other functions. Branch to function this, then branch to function this, then again branch to function this, and so on, right? This pattern suggests that each of these branch calls correspond to a separate jailbreak detection, meaning these functions are likely responsible for performing the individual detection methods. And if our assumption is correct, we should see a total of 10 such function calls, since in the application we have 10 total jailbreak detection mechanisms present. So let's verify this. The first call we have is over here, then second one, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th, and then it's returning. Indeed, we have 10 such methods. So now we have successfully identified all the methods responsible for each individual jailbreak detection. Now let's analyze these functions one by one. Our goal is to understand the logic behind each detection method. So once we break down how these functions work, we can then create a Frida script to work around these detections. So the first method responsible for this first jailbreak detection is this one, right? Function 61D0. Let's click on it and let's double click on this function, and it will take us to the definition of this function where it is defined. So here is the disassembly for this function, and at first if you look at it, decompile code which Ghidra generated, and from here you will notice that a function offset is being stored in this local underscore 38 variable, and later we can see a call to dispatch async. This indicates that this function, which is present at 624C offset, is being executed asynchronously as a part of a background task. This means that the jailbreak detection logic is running in the background, which is present in this function. So let's see what's inside this. If you simply double click on it, it will take you to that function. And let's quickly see the control flow graph, and yeah, this one looks interesting. There are a couple of branches as well. Mac ports lookup, XPC pipe, okay. Dictionary create, XPC pipe routine, alright. XPC dictionary get string, okay. Let's also try to see its decompile code to get a better understanding about this function. Stay alert as this can get complex because it is using Apple's SPC service for detecting the jailbreak, okay? And the best way to figure out what is going on in the code is by closely observing all the imported functions and any other symbol which is visible over here. In this case, we can first notice that there is a pointer to OS alloc1's table, which is then passed to this OS alloc1's function, right? To understand this, we need to first break down what this function does. The OS alloc1's function is similar to alloc and is used to allocate memory, but only once. The key point here is that if memory has already been allocated to this pointer, then it won't allocate a new memory again. And the OS alloc1's table is essentially a structure of type OS alloc1's S. Now this API is part of Apple system libraries, but it is private and is not officially documented. However, some open source projects utilize this API, so if you are interested, you can explore those to gain a deeper understanding. For now, let's move forward and analyze the application's flow. So after this OS alloc once, we have this comparison instruction, right? Here it's basically checking if the return value of this OS alloc once function is 0 or not. And if you know, in ARM64 architecture, according to the calling convention, the return value of a function is always stored into x0 register, right? So that's why here it's comparing it with x0. If x0 contains 0, then it is going to take this path, otherwise it will go to this block. Okay. Then we have a function call being made to Mac ports lookup. This one. Here it's passing Mac task self as one of its argument, right? Now Mac task self returns a special Mac port that represents the current process task. The purpose of Mac ports lookup function is to retrieve an array of bootstrap ports assigned to the process. If you are unfamiliar with bootstrap ports, they serve as communication channels between a process and other system services on iOS and macOS. So basically these ports enable applications to request services, manage daemons and interact with system processes, and this plays a crucial role in inter-process communication. In simple words, if one application wants to access some data from any other application, it uses this inter-process communication technique where both the process have this MAC port through which they exchange XPC messages.
So consider that we have these two processes, process A and process B, where process B is our launchd process, which is responsible for launching the applications from the launcher UI. When you click on the jailbreak detector application, launchd process will spawn a new instance of the application, and at that time it passes some MAC ports through which you can exchange information between process A and process B. Okay. Then from our target application, when we make a call to this Mac ports lookup function, it will return us an array of ports which are passed to this process. Okay. So usually the very first port is the one which is the bootstrap port through which we can access or request data from launchd daemon. So once we have access to this port, using XPC pipe create from port function, we can create a pipe between these two processes by passing this very first port as an argument to this function. And once the pipe is created, we can then exchange XPC messages back and forth in a secure manner. So at a high level, this is how this whole inter-process communication works.
After this, we can see there is another function call to XPC pipe create from port. This function creates an XPC pipe using the retrieve bootstrap port from the previous step. Okay, so what I just explained, to exchange data between the two processes, it communicates through these MAC ports, right? So over here, it looked up the MAC port for the current process, which is written by this function and stored into this variable. And then through this function, it's basically creating a pipe to that port so that it can send the XPC messages to that port. So by calling this function, it establishes a communication channel with system services. In this case, the application might be trying to retrieve some information about the jailbreak. After this, in this control flow graph, if you follow along these paths, we can see that if this function XPC pipe create from port, so like I said, in ARM64 architecture, the return value is always stored into X0 register, right? So after this instruction, here it's basically storing the result which is in the X0 register to this memory location pointed out by this address X20 plus hex 18. And then it's making a comparison with the value which is at that location, and if that value is 0, it will take this path, otherwise it will come over here. So if it's 0, from here again there are some comparison instructions, and eventually it's leading us to the end of the function from where it's returning, right? So let's just assume that this function is not returning 0 and it's coming to this block, and over here it's actually calling another function called XPC dictionary create empty, and then it's setting up some values into the registers and then calling another function called XPC dictionary set. It's not clearly visible in the control flow graph, so let's see over here. Yeah, it's XPC dictionary set uint64, and right before this function call we can see the value it is trying to set in the dictionary, that is JB domain. This is a hard-coded string, and similarly there is another XPC dictionary set uint function call wherein it's passing this action as one of its argument. So here basically through these XPC dictionary, it's creating a dictionary containing these two strings as values. After setting up these two values in the dictionary, it is calling a function called XPC pipe routine with flags. So this was the key information which we were looking for. And after this function call, if this condition is satisfied, it will call this XPC dictionary get string, wherein it's looking for the root path. So on a jailbroken device, you will get this root path in the reply of the XPC request made using this XPC pipe routine with flags. So when you query for this JB domain and action, which we have set using these two methods, you will get this root path as a reply. So in case of rootless jailbreak, we will get some path other than the root path, which is slash. And in case of rootful jailbreak, we will get slash as the root path. Okay, so one thing we can try is to hook this XPC dictionary get string function and see what we are getting as the root path on our rootless jailbroken devices. So let's try that first. So here we have the application, and here I'm gonna open VS Code, in which I'm going to create a new script called mitigate jailbreak.js. All right. Now we are gonna hook this function, which is an imported method, right? So we can use interceptor.attach API of Frida, and then to resolve that XPC dictionary get string method, we can use module.find export by name followed by the name of the function. This is the name of the function we want to hook, right? So this Frida API module find export by name basically gives us the address in the memory where this function is located. And then to create a method body where we have to define two callbacks. First one is onEnter function, which takes args as its argument. So this onEnter callback function will be triggered whenever this XPC dictionary get string method is called, and whatever the arguments that was passed to this method, we can access them through this args argument inside this callback. Okay, for now let's just put a log which says hooked XPC dictionary get string, and then there is another callback which is on leave function, and it has this return value as its argument. So whatever the value being returned by this function, we can access that through this return value argument inside on leave callback. Okay, so first of all, let's just print another log which says original return value dot read utf-8 string, and that's because this function will return a string containing the root path. Okay, that's it. Let's save the script over here. Let's go back to the terminal, clear this out, and okay, we are currently inside the jailbreak detector app and our script is in the root directory. So here, okay, I created outside this folder, so let me just move it inside it. So now we should have this script over here, right? And let me just enable my environment where I have Frida installed, which is inside FatalSec environment. Activate. Now to launch a Frida script, we should first know the package name of this application, right? So there are a couple of ways to do it. The easiest way is to use Frida ps command -uai, and this will list out all the package names of the applications which are installed on your device. So I have this jailbreak detector application on which we are currently working on, and its package name is this one. So let's just copy it, and now to launch the application, we have Frida-u-l, the name of the script, which is mitigate_jb.js -f to forcefully spawn a new instance of the application followed by the package name of the application. And there we go. You can see over here that this function is getting called multiple times even before we have clicked on this detect button. So this means that by default, when an application is launched, it tries to communicate with some other system services and try to get some values through this XPC function call. Okay, so for now, let's just ignore these and let's observe what it returns when we click on this detect button. So let's just click on it. xpc get dictionary method is called, and our hooked is also triggered, and this is the value returned by this root path. So this suggests that it's a dopamine jailbreak which is installed on the device, and this is the root directory for it. Ideally, application should check for this path before making the decision. However, if you observe over here, after calling this function, it's not storing its return value anywhere, right? It's not assigned to any local variable. This means the application is only calling this function, but it's not relying on its return value. To make it more clear, in the decompiled code, you can see the value returned by this function is stored into this ivar4 variable, and then it's being compared. If it's 0 and there is another condition which is being compared, then it will call this and it will set a flag variable to 1, suggesting that the detection is triggered. Otherwise, it will set the local variable to 0. Okay. So if we try to hook this function instead and try to manipulate its return value to a non-zero value, because here it's being compared with 0 and there is an AND condition. So if we make this value non-zero, this whole condition will fail and it will come to this else part where it will set the flag to false, indicating that jailbreak is not detected. Let's try that. Going back to the script. So this is of no use. Let's modify this, and let me just copy the function name from here, which is xpc routine with flags. Copy, paste. Okay. And now in the on leave, we know it's not a string value, so let's just remove it and print directly the return value. And basically now we want to manipulate this return value to a non-zero value, right? So for that we can use return value dot replace method, and let's just put 1. Okay, and let me put another log just to make sure that it's modified. Manipulated return value. All right, let's save this script now. Go back to the terminal. Here is the application. Exit, clear, and let's launch the application again. Here it says expected a pointer at line 10. Okay, let's see. Oh yeah, we don't have to include this underscore. Save, exit, clear, and launch it again. All right. Now let's see what happens when we click on this detect button. So in the logs, you can see that the hook triggered. Original return value was 0 and the manipulated return value is now changed to 1. And in the applications UI, you can see the status of the jailbreak detect one method. It's changed to this green tick, which means we have successfully managed to work around this jailbreak detection method. Great. Going back to Ghidra, and let's now move on to the next detection. So again, let's just go back to the symbol table, and here we have this method run detection methods, right? And inside it, just now we analyzed this function and saw how to overcome the jailbreak detection 1 mechanism. Now let's move on to the second jailbreak detection method, which is function 40c4. Over here you can observe the same behavior. There is this asynchronous call being made, wherein it's trying to call this function as an asynchronous task, right? So this function should be the one which contains the real logic behind the jailbreak detection 2. So let's go inside it, and there we have it. So it looks pretty big, and immediately we can observe something interesting. There is a function 7640 which is being called multiple times, right? And if you observe the arguments which are being passed to this method, you will know what this function is trying to do. As you can see, it's taking a class is called string encryption as its first argument, and then we have the encoded or the encrypted string being passed as another argument. So based on this, we can assume that this function is trying to decrypt these encrypted strings, right? So there are a couple of them. All of these hard-coded encrypted strings are being decrypted over here. Okay, so if you are interested, you can try to hook this function and intercept the values being passed to it to find the strings in plain text. But for now, let's just see what the function is doing after decrypting these strings. So after all these string decryption methods, let's see in the control flow graph. So yeah, this is a pretty big basic block where it's trying to decrypt all the strings one by one. And then here gonna come to this basic block where you can see that we have this SVC instruction present, which is running inside this loop, right? So to figure out what exactly happening over here, you have to first know what this SVC instruction is and how to read it. So for those who are unfamiliar, this SVC instruction, which is known as supervisor call, is a mechanism used to switch from user mode to kernel mode, allowing you to access privileged system resources. For example, if an application needs to access a file which is stored on the device, it would use an SVC instruction to invoke a system call like open or any other file related function. In iOS applications, developers often use this technique to hide or obscure the actual function being called, making it harder for attackers or reverse engineers to determine its purpose. In this case, simply by looking at this disassembly, it's not immediately clear what's going on over here, and you cannot tell just by looking at it which function is getting called over here. So this basically adds an extra layer of complexity to reverse engineering efforts, unless you know how this SVC instruction works. So here you can observe that before making a call to SVC instruction, it's setting up some registers like moving x11 to x0, then moving x10 to x1, then moving x21 to x16, right? So for a system call to work, we first have to set up a system call number. In operating systems, system call numbers are predefined and hard-coded into the system, and based on this system call number, kernel decides which function to call in kernel space. So in iOS, this system call number is stored into x16 register before making a supervisor call. Okay. In this case, it's storing hex 21 to x16. So this is our system call number. And to figure out which function is being called, we can see which function is associated to this system call number. And for that, we can have a quick look at the Unix system call table, which you can find over here. So here we have list of system calls starting from iOS 6.0 version. Link to this I will also put in the description box. So the system call number our application is trying to set is hex 21, which is 33 in decimal. So let's go back to the browser and see which function corresponds to 33. So at 33 we have access function. All right. So now we know that this SVC instruction is trying to call access function. But what about the arguments which are required by this access function call? Well, they are also stored in the registers starting from x0. So basically for access function, we know that it takes two arguments. First one is the path name, which is the file path it wants to access, and the other one is the mode. So we are interested in the path field because we want to know which files or path this function is trying to access. And according to ARM calling convention, we know that the first argument is always stored into x0 register, which is being set over here, right? So to intercept that, what we can do is we can hook onto this instruction or the instruction after this, which is present at, yeah, the offsets are not clearly visible over here. So let's head back to the disassembly. So this instruction is located at 4F74. The reason why I am not hooking on this instruction is because I want this instruction to be executed so that the value in x0 register is set, and then after that I will hook and read the value of x0. Okay, so let's do that. In Frida script, first we have to figure out the base address where the application's binary is loaded into the memory. So when we launch the application, every time a different memory location is assigned to our application because of ASLR. So that's why we can't hard code it, and we have to figure it out at runtime. And luckily in Frida, we have a API called process.findModuleByName, and here you can provide the name of your application. In this case, it's jailbreak detection. Let's store it into a module variable. So this Frida API will enumerate all the modules which are loaded in the memory by the current process and will return the module object for this particular module name. Now inside this module, we will have all the details about this module, including its base address, its size, its path. Okay, so let's just print it in the log. So the module name you can access through this module object directly by accessing the name attribute is loaded at, and then the base address again you can access directly by this module object by accessing its base attribute. Okay, let's save the script. Okay, and now what we want to do is we want to set up a hook at this offset, right? Let's copy it. Oh, and one more thing. The reason why I am not including this whole offset is because this image address is being set by Ghidra and it's not the real offset. To fix this, what you can do is if you click on this icon which says display memory map and then click on this home button, it will show you the base image address where the Ghidra has loaded your binary. Okay, and you can just change it to 0. Okay, it will do the relocation fix up. Just ignore this error and that's it. Now you have the real offsets visible. So this is the offset. I want to set up my hook, and to attach the hook we have interceptor dot attach API, right, followed by the address. Now this is just the offset and not the actual address in the memory. So to figure out the actual address, what we have to do is to add this offset to the base address of the application, right? And here we have already calculated the base address, so we can use this base address and then add our offset to it. Now this will give us the actual address in the memory where that instruction is present, and then we can create a function in which firstly we can simply put a log which says svc. We know now that the svc instruction is trying to call the access function, so let's just put access and then the argument which we want to read, which is inside the x0 register, and we know that it's of type string, so let's just read it as C string. Okay, let's save the script now, head back to the terminal and let's launch the application. Enter. So it says cannot read property name of null at line number 2. Okay, that's because the name of the module is jailbreak detector, not the detection. Let's save it, clear, launch it again, and now you can see our log is being printed over here. Jailbreak detector is located at this address. So this is now the base address of our application, and let's see what happens when we click on this detect button. So you see now this was the first hook we set up earlier for the jailbreak detection 1, right? And after that our second hook got triggered, and the part which access function is trying to access are var log apt and var log dpkg. So on a jailbroken device, these are the packages which are generally present on the file system. So this way, by making use of Frida hooking, we can see the paths which are encrypted without even decrypting them, right? So during the static analysis, we saw that there were a lot of encrypted strings which we don't know what they are, but then after decryption they are being passed to this access function which is being called through the supervisor call. Okay, so now we know what the application is looking for. Let's make a blacklist where blacklist, it's going to be an array because there are multiple paths, and let me just copy these paths from here. First one is var log apt and the second one is var log dpkg. Okay, and inside the hook we can simply check if blacklist contains any of the value which is being accessed by this access function call. So whatever the paths being checked by the access function through svc instruction, we will check whether that file path is in our blacklist or not. If it is in the blacklist, we will simply try to manipulate it. For manipulating the file path which is in the x0 register, we can use write utf-8 string method directly on it, and here let's just put not exist as a path. So you can put any. So this will basically tell the application that the path which the access function is trying to access is not present, and as a result application will think that okay, the jailbreak paths are not present in the file system, and it will most likely be fooled to think that jailbreak is not present. And for troubleshooting purpose, let me just put a log over here as well, which says manipulating x0 this dot context dot x0, and then read it again just to be sure that the value is modified in this x0 register. Save the script now, head back to the terminal, launch the application again using Frida, and let's see what happens now. Okay, in the log we can now see that application is trying to access another file, which is var lib. And for these two paths, apt and dpkg, you can see that the path is manipulated to a non-existent path, right? And if you remember from the control flow graph, yeah, so you remember this is being called in a loop. So what's basically going on over here is that it's trying to call the access function and trying to access file paths one by one, which are decrypted by these decryption methods. Okay, and if any one of the path exists, it will simply come out of this loop and execute this block. Okay, so that's why after modifying these paths, we are now getting another path which is being accessed, and most likely this also exists on our device. That's why the detection got triggered. So let's add this as well in the blacklist. Save, head back to the terminal, and let's launch the application again and see what happens this time when we click on the detect button. Now we can see in the application that this detection is also passed, and in the logs we can observe some other paths which are being accessed now. And the reason why we are not getting any more detection is because these paths simply does not exist on the device, but in case on your device, if these paths exist, they will cause the detection. So simply add all these paths into the blacklist array which we have over here in our Frida script, and then you should be good to go. Let's move on to the next detection. So if we go back to the run detection methods and go to the third function which is responsible for jailbreak detection 3, again we can observe the same pattern, right? Through this dispatch async function call, it's trying to call this function as a background task. So let's see what's inside this function, because this should contain the real logic behind the jailbreak detection 3. So again, firstly we have these function calls, and here again you can observe that in the first argument this string encryption class is being passed, followed by these encrypted strings, right? So again this function is first trying to decrypt these hard-coded encrypted strings, and after that again it's calling a supervisor call through this svc instruction. And if we have a look at its control flow graph, it's running in a loop, right? So this suggests that whatever the function which is being called over here through this svc instruction, it's being called inside a loop wherein it's trying to iterate over all these values which are being returned after decrypting these hard-coded strings. Okay, so yeah, it's a similar behavior or the pattern which we observed in the previous function as well. And I'm hoping that you know by now how to read this svc instruction. So in iOS, the system call number is stored into the x16 register, and here in x16 register through this move x16 comma hex 21, it's storing this hex 21 system call number into x16 register, right? So this hex 21 is nothing but 33 in decimal, and we already saw that 33 system call number belongs to access function, right? So again the application is calling access function over here. So let's just try to attach the hook at this offset, the next one, after it initializes the x0 register, which should contain the first argument to this access function, which is the path name, right? Let's head back to the disassembly and attach the hook at the next instruction, which is 47D4. Let's copy this offset, call the interceptor attach API again, and to set up the hook we have to add it to the base address like this. And then inside this function body, we can simply print a log. So it's a svc instruction and we know it's access, and the argument is in x0 register, which is of type string. So let's just read it in string form using readc string method. Okay, let's save the script now. Head back to the terminal. This is the application and let's launch it again. So far we have managed to bypass these two detection, and let's see what happens when jailbreak detect 3 method gets called. So if we click on this detect button, you can see that there is a new svc access hook triggered where it's trying to access this file path where lib filza. Filza is basically a file explorer which is usually present on a jailbroken device. So you can see over here in my device I have Filza which is installed already, right? So this is what it is detecting. And using this file explorer application, you can easily navigate between different files and folder, including the root folders. So let's just add this file path in a new blacklist variable for this hook. So let's create a new blacklist, let's say blacklist 2, and add this path over here, and we can again use the same logic. So let's just copy and paste this. Instead of blacklist, it's going to be blacklist 2 now, and that's it. So again we are checking which file path is being accessed by this svc instruction, and if it's present in our blacklist array, we will simply modify its path to a non-existing path, and that should help us in mitigating this detection. So let's go back and launch the application again using Frida. Let's see what happens now. Detect. Yeah, the detection is still not passed, but in the log we can observe that whenever this file path is being checked, it's modified to a non-existing path, and now another path is being checked by the application, which is where mobile library filza. So let's copy and add it to this blacklist array. That's all you have to do. Save the script, exit, and launch the application again. Click detect. Awesome. In the application now you can see that the jailbreak detection 3 is passed, and in the logs also we can observe now that when the application is trying to access this filza path, it's modified to a non-existing path, and then it's trying to access another path related to filza, but on my device this path does not exist, so that's why this detection didn't get triggered, and that's why we have this jailbreak detect 3 being shown as passed. In case on your device this path also exists, you just have to add it to this blacklist array and you should be good to go. All right. Okay, let's move on to jailbreak detection 4 now. And in the application you can see that it's already showing as passed on my device, but in case on your device, if you are using another variant of rootless jailbreak, this could be detected. So let's quickly see the logic behind this detection as well. Going back to Ghidra, and let's head back to run detection methods. So the fourth function we have is this one, right? Let's go inside it. Again, the same pattern. We have this dispatch async function, which is trying to call this function as a background task. And if we go inside this function, firstly, it's trying to call again the string decryption routine, where it's trying to decrypt these hard-coded strings. And after that, let's see what's going on. So you can see that there is a function called bootstrap lookup which is being called in a loop. So this function is actually a iOS or Mac OS system function which is used to look up a Mac service. And on a jailbroken device, there are some services which are present as a part of the jailbreak process. So using this bootstrap lookup, it basically tries to look up those Mac services which are passed as an argument to this function. So most likely what's happening over here is that this application has some hard-coded Mac service paths which are present in this application's binary but in encrypted form. So through these string decryption routines, it's first trying to decrypt those Mac service paths, and then it's calling this bootstrap lookup method and passing those paths one by one inside this loop, right? and if any of those paths exist, this function will return a non-zero value. Again, this API bootstrap lookup, it's not documented by Apple and it's a private API, so you will not find its official documentation. But here from the decompiled code, let me try to explain you what the syntax of this function. So the first argument which is being passed to this bootstrap lookup function is bootstrap port. It basically allows processes to look up and communicate with system services. So it's the same port which I explained you in the first detection technique, which was related to inter-process communication, right? Then the second argument is the service name. So in the second argument, you will find the service name which is being checked by the application to detect presence of the jailbreak. So based on this, the application is trying to detect whether the rootless jailbreak is present on the device or not. So one way to figure out what these services are and eventually to work around these detections, all you have to do is to hook this bootstrap lookup method and intercept its second argument. Okay, let's try that. Going back to VS Code, and let's create a new hook using interceptor.attach API. This time we want to attach the hook on an imported function, so we can use module.findExport by name API of Frida. First argument is going to be null because we don't know in which external library this method present, and then the name of the method, which is bootstrap lookup. Let me just copy it from here and paste it. Make sure you don't put the underscore which is visible over here, otherwise the hook will not work. Then the function body, where we have two callbacks. First one is on enter function. This takes args as its argument, and then the other one is on leave function, which takes return value as its argument. Right now, inside the on enter, which will be triggered as soon as this function is called, let's just put a log first which says hooked bootstrap lookup. Okay, and we want to analyze the second argument of this function, right? So let's just print it over here itself, and the list of arguments you can access through this args argument. So it's an array basically. So if you want to access the first argument, you can access it using the 0th index and so on. So in this case, we want to access the second argument, which we can access using the first index of this args variable. And this service name is actually of type string, so we can read it as C string. Okay, let's save this script now. Yeah, I think there is no need for on leave. Let's remove it. Save, head back to the terminal and launch. All right, yeah, the first thing you can observe in the logs immediately is that this bootstrap lookup hook got triggered even before we clicked on the detect method. So for now, let's just ignore these calls and let's see what happens when we click on the detect button. We can see that these hook bootstrap lookup hook got triggered multiple times, and it's basically trying to access these services: substrate, jailbreak D, OPA, jailbreak D, right? So on my device, these services does not exist, and that's why this detection is showing as passed. But in case on your device you have any of these modules installed, this detection would have been triggered. To work around that, what you can do is simply create a new blacklist array, let's say 3, and add these paths to it. So let me just copy it and paste it over here. Then the second path is this one, copy paste. Then the third one is this one, paste, and then the fourth one is this, copy paste. And the logic is going to be same, so I'm going to copy this if condition, paste it over here. Instead of blacklist 2, we have blacklist 3, and instead of x0 register, we can access the argument using this args1, right? So let's just replace this x0 with args1, and that's it. And it's not a path, it's a service name, so instead of slashes we can put dot. So now what will happen whenever the application tries to look up any service related to jailbreak and which is in our blacklist, it will modify it to non-existing service, and this will lead to mitigate this detection. Let's save the script and exit, clear, and launch it again. Okay, let's see what happens when we click on the detect button. Obviously, in my case, it was showing as passed, so there is not going to be any significant change. But in the logs, you can see that now whenever the application is trying to access these service names, it's replaced by a non-existing service. Okay, head back to Ghidra. And let's now move on to the next detection, which is jailbreak detection 5. So inside this, for jailbreak detection 5, we have this function, right? Let's go inside this function, and over here we can see the same pattern. Through this dispatch async, trying to call this function as a background task. So this function is actually the function containing the real logic behind jailbreak detection 5. So let's go inside it and analyze it. Here at the beginning, you can observe that it's calling this same routine which is responsible for string decryption, right? After that, there is another method being called before making a call to the supervisor instruction svc. So this is the function for string decryption, and after decrypting this string, it's making a call to this function. And then whatever the value being returned by this function, that will be stored into x0 register by default according to ARM64 calling convention, right? And then return value is then stored into x0 register again. Okay, so basically whatever the value being returned by this function, that will be stored into x0 register, which is then passed to the function which is being called through this svc instruction, right? So you know now how to read the svc instruction, right? So the system call number here it's storing into x16 is xbc, which is nothing but 188 in decimal. So let's see which function corresponds to this system call number. Over here in this table at 188, we have stat function. Through this svc instruction, it's making a call to the stat function, and according to the syntax of stat function, the first argument of that function is the path. And let's quickly also see what this function is doing. So inside this, it's calling this utf8 string method using objc message send. This technique is called reflection, where instead of calling the function directly, you can call it using objc message send. So basically it's calling utf8 string, and what we can assume using this is that that after decrypting the string, it's encoding that string into utf8 form. Okay, and then it's passing it to the stat function. So let's attach the hook to this instruction to figure out which path is being checked by this stat function. Let me just copy this offset, and if I go back to the script, we can create a new hook using interceptor.attach module.base.add offset, and then the function body. Let's just put a log over here indicating that as we see stat hook is triggered, and we want to print its first argument, which is in x0 register, and it's in form string. So let's just read it as string using readc string method. Let's save this script, head back to the terminal, and launch the application again using Frida. Hit tag button and see what do we get. So in the log, you can see now that as we see stat hook is triggered, and it's trying to access this path, USI standalone firmware. Okay, let's go back to Ghidra and see the control flow graph. So here it's trying to access that firmware path using the stat function, and then the result of that stat function is stored into this x24 register. Then there we have a comparison instruction, compare branch on non-zero. So what this instruction will do is it will check the value inside this w24 register. Based on this, if w24 register contains 0 or not, it is deciding which branch to take, either this one or this one, right? So if x24 or w24 contains 0, then it will go to the next instruction, which is this block. Otherwise, it will go to this block directly. So if we modify the argument to this stat function, in such a way that stat function is not able to access it, then the W24 register will contain a non-zero value. As a result, this path will be taken and it will skip all this logic. So let's just try that first. So we already have our hook attached. So we can directly modify this value inside this hook using write UTF-8 string method, and we can put a non-existent path like this. And then for troubleshooting purpose, let me just put another log which says manipulating x0 and then the value read C string. Let's save this script, head back to the terminal, and let's launch the application again using Frida. Now let's click on the detect button and see what happens. And it says not a function at line 48. Yeah, okay, there is a typo, it's capital U. Click on detect button. Okay, in the application still this jailbreak detect pipe is being detected, but in the logs you can observe that when this firmware file path was accessed by this stat method, we have manipulated it to a non-existent path. So this should mitigated this detection, but because the application is still showing that it's detected, this means that there is some other check being present which is getting triggered. So let's see, going back to Ghidra. So what we did so far is that when this SVC call is triggered, we have modified its value in such a way that stat function will return a non-zero value. As a result, this W24 will contain a non-zero value which forces the application to take this path, right? And in this path, we have another string decryption routine being called, after which again we have a function call followed by the svc instruction where it's trying to call this function which corresponds to stat function, right? So what we can do now is we can again do the same thing. Let's attach the hook to this instruction where it's setting up the x0 register, and then let's see which path it's trying to access. Let me just copy this offset, going back to the script, calling interceptor dot attach API again, adding the base address to the offset, defining the function body, and inside this let's just put a log suggesting that svc stat 2 is being called, and we want to print its first argument as a string. Let's save it and spawn the application again using Frida, and let's see what happens now. So in the log this time, after the first stat function call, it's calling stat2 function where it's trying to access /private/preboot directory. So if we just modify this argument which is stored in x0 register before this svc instruction get executed, we can work around this detection. So let's just try to do that. We already have our hook present, so over here we can simply